Let's take a look at what happens when k is very small. When k is very small, it turns out that it can be difficult to graphically identify the x values. But we don't need to worry about that, because if k is very small, then the change is going to be very small. And it's going to be so small that we don't even have to worry about it. What do I mean we don't have to worry about it? Well, let's take a look at this problem. Let's say my initial concentration is 0.1 molar, and we remove x, so minus x, and that x is 2.3 times 10 to the negative 6. Well, what's the final concentration of A? Well, if I set this problem up and I do the subtraction, remember our significant figures rules are such that we can only go that far and then we round. So we're going to round all the way back to 0.1. Did we lose some A? Yeah, but not enough to be significant. It turns out that that's going to simplify things mathematically for us. So let's take a look at a problem that has a very small k. We have a half-liter reaction vessel with 0.13 moles of hydrogen sulfide, that's our reactant, at this temperature. We want to know the equilibrium concentrations. So I can write my equilibrium expression, h squared times h2 squared times s2 over h2s squared. I can find Q. There are no products initially. And 0.26, what's that about? It's 0.13 divided by 0.5. It has to be molarity. That's where my 0.26 comes from. So it's 0 over 0.26 squared is 0. So clearly my reaction goes towards the products. So I set up my Rice table. 0.26, 0, 0, minus 2x plus 2x plus x. 0.6 minus 2x, 2x, and x. Okay, no problem there. And then I set up my substitution. And I see I have 1.7 times 10 to the negative 7th is 4x cubed over 0.26 minus 2x squared. And yeah, I could bring that over and it's just going to be hard. And especially on a graphing calculator, but even on Desmos, when you have k's that small, it becomes really hard to find the root. So we're going to simplify. So here is my assumption. I'm going to assume that because k is really small, only a tiny amount of hydrogen and sulfur will be formed. That means only a tiny amount of H2S will disappear. So I'm going to say that 0.26 minus 2x is still going to be about 0.26. Let me say that again. 0.26 minus 2x to the two significant figures of my problem is still going to be 0.26. So now my problem is, I multiplied these two together. 1.15 times 10 to the negative 8th is 4x cubed. Solve for x. Well, did my assumption work out? Well, let's take a look. 0.26 minus 0.0028 to the hundredths place is still 0.26. It worked. .0028 is 2 times x. hydrogen 2x, 0.0028, sulfur x, 0.0014, and I even decided to go back and double check. Let's plug these numbers back into my calculator, and it's still 1.7 times 10 to the negative 7th. So the math is simpler. I don't have to worry about my graphing calculator or my Desmos. I don't have to worry about the fact that those don't work very well when k is super small. I don't have to deal with the fact that I've got a cubic and a quadratic and all sorts of icky, nasty math going on. All because I assume that my initial minus 2x is still going to be about the same as my initial. Now in this problem, I also have a very small k. So why don't you set up the equilibrium expression and try to make that simplification, and then we'll go over it. Okay, so hopefully you were able to write the equilibrium expression and find Q is 0, so it has to be going towards the right. So I set up my Rice problem, 0.2, 0.30, minus 2x minus x plus 2x, 0.2 minus 2x, 0.3 minus x, and 2x. Then I plug it back in. Ew. This doesn't look like fun. 0.2 minus 2x squared times 0.3 minus x times 2.5 times... Well, this I can do. 4x squared. That's not too bad. If I make the assumption that 0.2 minus 2x is still going to be 0.2, okay. And 0.3 minus 2x is, 0.3 minus x is still going to be 0.3. Why am I making those assumptions? Again, I'm assuming that because k is very small, very tiny amount of C will be produced, which means very tiny amount of A will disappear and a very tiny amount of B will disappear. If a very tiny amount disappears, then that's smaller than the significant figures of the problem. 0.2 minus 2x is still 0.2. Let's double check. I have 0.2 minus 2x. Well, to the significant figures of the problem, I can only go to the hundredths place. That's still 0.2. 0.3 minus x, still 0.3. And 2x, 5.4 times 10 to the negative 6th molar, which, perfectly fine this way, but it also happens to be 5.4 micromolar. Now, how do we know when we can use the simplification? Well, first, we're going to use what's called the 5% rule, meaning if the x we end up with is less than 5% of the initial amount of reactant, then it works. Why does it work? Well, because equilibrium constants are typically plus or minus 5%. So that's within the error of the equilibrium constant. But in order to know that, I have to solve the problem. So how do I know whether to try the simplification without already solving the problem? If my initial molarity is 1,000 times bigger than my equilibrium constant, give it a try. Once in a while, that simplification won't work, but most of the time, if the initial molarity is 1,000 times bigger than my equilibrium constant, it works. Now here is the key part. You can ignore x when you're subtracting it or adding it. because we have an amount minus something that's smaller than the significant figures, and an amount that's big plus something that's smaller than the significant figures of the initial. Those are okay. If you see an x or a 2x or a 2x squared or anything like that, you cannot ignore it and drop it off. So let's take a look at a couple of problems. The first thing I want you to do is pause the video and decide. If my equilibrium constant is given here and my x is given here, does the 5% rule work? Either check yes or no. For the first one, we end up with about 2%. X is about 2%. How did I figure that out? 5 times 10 to the negative 6th over 2.5 times 10 to the negative 4th times 100 is 2%. For the next one, it's a really, really small percent. I don't even remember, but I just remember it's being super small. And then for the last one, it's about 10.8%. So no, we can't use the simplification for the third one. We can use the simplification for the first two scenarios. Now take a look at this next set, and we have an initial molarity and we have an equilibrium constant. Decide, based on the initial molarity and the equilibrium constant, whether or not you're going to attempt to use the simplification. In this case, only one of them would really work for the simplification. In the first case, we can't have the equilibrium constant be bigger than the initial molarity. The whole point is that the equilibrium constant has to be smaller. And for these two, yes, the equilibrium constant is smaller than the initial, but not by that much. So the only one that would let us use the simplification is this third sample. And for the last set of problems on this page, cross off all the x's that can be ignored. Check the answers when you're done. So we can cross off this one, and this one. We cannot cross off any of the other x values. So hopefully this page gave you a sense of when we can use the simplification. Now let's try one more problem. When nitrous acid is dissolved in water, it forms hydronium ion and nitrite ion. And nitrous acid is a weak acid, and it has an equilibrium constant of 7.2 times 10 to the negative 4th for this reaction. So if I start with 0.5 molar nitrous acid and 0.4 molar nitrite, pause the video and calculate the equilibrium constants of everything in the problem. Remember, if it's a pure liquid, it is not part of the equilibrium expression. So take a second, try it, and then turn the video back on. The equilibrium expression, products over reactants, is right here. And if I look at my Q for the initial values, I have 0 times 0.4 over 0.5, so it's 0, so it has to go towards the right. So I set up my rice table. I have 0.5 minus x, 0.4 plus x. So now I plug in the numbers to the equilibrium expression, and I see that I have a 0.4 plus x, 0.5 minus x, It's doable, but I'm going to use my simplifications. 0.4 plus x should be approximately 0.4. 0.5 minus x should be approximately 0.5. And it simplifies to this. Now I can calculate my x, and I can see that my nitrous acid is 0.5 minus 0.0009. That's still 0.5. My simplification worked. Nitrite is 0.4 plus 0.00090. To two significant figures is still 0.4. So that simplification worked. And hydronium is 9 times 10 to the negative fourth molar. Again, two significant figures. And what we're going to see in the next unit when we look at acids and bases is that now we're going to be able to find the pH using equilibrium. I hope that learning about this simplification when we have a very small k will make some of the problems easier. As always, if you have any questions, let me know.